Okay, so I just wanted to spend a couple minutes talking about applications, actually, before I go on to other solution techniques. So first of all, a spring. So if you were to write, if you were to write MA, if you were to write MA is equal to the net force, you'd recognize that as Newton's second law, right? So if you have MA is equal to minus Kx minus beta V, let's see here, and then plus an external force, then you rewrite this, well, A is equal to x double dot, V is equal to x dot, using old Newton's notation. So what you got is mx double dot plus beta x dot plus kx is equal to the external force, or as we usually write, mx prime prime plus beta x prime plus kx is equal to the external force. And so this differential equation describes a spring with a mass attached to it that's going through some sort of medium, which puts a linearly velocity-dependent friction force on it. It's kind of the most simple kind of thing. People call these things dash pots or whatever. So if you have m not equal to 0 and beta and k greater than 0, and you put a constant force, you can basically do undetermined coefficients, and you'll get the homogeneous solution plus the constant force divided by k. So it's pretty much just like it's, I think you can even redefine the variable y as x equals minus f naught over k, and you'll basically get back to no force at all. That actually just, if you have a constant force, you can define new variables such that, again, you have my double dot plus beta y dot plus ky equal to 0. This would be the situation with like a mass hanging from a spring. If you have a spring and a mass and some kind of jello or whatever, and it's oscillating this way, and then you were to take the same apparatus and make it vertical, the equations of motions are not changed. It's just the equilibrium for the spring is stretched, it's shifted because of gravity. Because gravity over a little vertical displacement is essentially constant. So it's like this. So I mean, there's an application of that. Pendulum. Well, not pendulum. We're talking about problem. Excuse me. So if you had a simple harmonic oscillator is when you have no friction. And so if I had mass 1, spring constant 1, if that was my force, my external force, f dot cosine 2t, the resulting motion ends up being f naught over 3 cosine t minus cosine 2t. Now this part is because of whatever initial condition I stated in this problem. And this part is actually the response to the external force. But you get a sinusoidal solution which mimics the force which you put on the spring system. Now, if on the other hand, I put a force on the same spring mass system that has the same resonant frequency as the homogeneous solution, then weird stuff happens. Then we have the method of annihilators kick in non-trivially. We have to put a t in our particular solution. We end up with a solution as in box, x equals cosine t plus t sine t. Well, of course, as t goes to infinity, what happens? You get this unbounded buildup of energy in the spring because you're coupling this external force to the spring. You're building the energy up and up and up and up, and of course, eventually the spring breaks, right? So this is pure resonance. So the next best thing to that you could think about is the case of a spring with friction, like this. You could think about m double x, ma plus beta v plus kx equal to this, where beta is not 0. In that case, we can't have that multiplication by t because the solutions for this are exponentials times sines or cosines, or perhaps pure exponentials, but we can't have a pure sine or cosine if there's a non-zero beta there. That's the structure of the solution set. So that means I can't get the t times sine or t times cosine. I'm not going to get something that blows up, but I am going to get something like, I can get a cosine and sine back again. So the particular solution will be bounded. So the question is, for a given f naught, right, what's the maximum response you can get out of the thing? as you say adjust to the gamma. As you adjust the frequency, what gives you the maximum response for a fixed amplitude force on it. And so I work it out. Find the particular solution, right? And I plug it back in, work out the math here. Eventually, I get to the particular solution of excuse me, xp equals to f naught over the square root of that stuff plus beta squared gamma squared sine of gamma t plus some, well, this is always fun. Maybe I shouldn't use this room. Stupid roof shaking. Gamma t plus a phase angle phi, right? And then of course to maximize that, you differentiate with respect to gamma and look for critical points. It's kind of awful, but you can do it. So dm d gamma gives you this. Now that will be 0 if the numerator is 0, which would be this being 0, which would be this equation, which would give you gamma as plus or minus the square root of 2mk minus beta squared over 2m squared. Assuming, of course, that this quantity here is what? Positive. And I have assigned homework problems inadvertently, which made that quantity negative, which means looking for the resonant frequency is a fool's errand. There is none. Anyway, so that's the so-called resonant frequency. That choice of forcing function, that frequency for the forcing function gives you the maximum response possible for that spring mass system. Yes, Linda? Yeah, it means there's no choice of gamma, which maximizes it. I think that in that case, gamma equals to 0 is an endpoint. 0 frequency is always an endpoint. I think that means that the constant force gives you the maximum, if I remember right. It's either that or it's. If dm d gamma is never 0, that means that either m is always increasing or it's always decreasing. So either frequency 0 is maximum or minimum, and frequency infinity is maximum or minimum. You don't need to consider negative frequencies because sine of gamma t is the same as sine of minus gamma t. It suffices to look at non-negative values to index what's possible for your solution set. Anyway, there's beautiful treatments of this in Nagel, Saff, and Snyder in section 4.10, or in Ritker and Rose's book, if you'd like to see more. What I did then, in my notes here, is to attack the same problem again from the viewpoint of RLC circuits. This is Kirchhoff's voltage law and current law, or I forget which one. I think it's the voltage law. Going around the loop for an RLC circuit with an external voltage source of epsilon, E, the electromotive force, if you like that kind of terminology. And so what I do, instead of treating it with sines and cosines, I feel a sneeze coming on. Excuse me. Blah. I complexify the problem. And if you study the solution in the complexified world, it's so much easier. Because then your particular solution, rather than being a linear combination of sine and cosine, is merely a constant times an imaginary exponential. I don't know about you, I would much rather differentiate imaginary exponentials than sines and cosines, 2 of them. So my particular solution is this: differentiate, bam, bam. Plug it back in. There it is. A is this over that. Done. It is stupid how much simpler the analysis is in the complex domain here. So, of course, I got to pick out real solutions and imaginary solutions from that to find the actual particular solution to the given problem. That's where the rubber hits the road in the complexification technique. But there it is. I get these particular solutions, and then I can massage those a bit to get back to basically what we had before. And so basically, the solution's the same. It's just that with a RLC circuit, L is like the mass, R is like the beta. I think 1 over the capacitance is like the spring constant. So there's a dictionary between these worlds. The resonant frequency we had for the spring mass system corresponds to this resonant frequency for the RLC circuit. And you can see the analysis is shared, the same mathematics by both systems. And anyway, I think this is an interesting bit of math. I have gone so far as to test this before. Not recently, though. And it didn't go well. I think I put it on a final one year. Golly. Why did I do that? I don't know. I'm not well. All right, let me put this away. Okay, so that's all I got for you guys on the applications front for the moment. I mean, we've seen some kind of exotic stuff in here in terms of solution techniques, right? The Cauchy-Euler problem. Those do come up in certain problems of mathematical physics. Cauchy-Euler problems do arise. And of course, but you see the constant coefficient case, which we solved with great ease and cleanliness, right? There's a very lucid, clear solution that exists for the constant coefficient case. That more often than not is what you need for the most ubiquitous examples in physics. I mean, the spring mass system, harmonic oscillators, generically speaking, if you're looking for local phenomena, you're near some potential well, right? So if you're close enough, your potential really just looks like 1/2 x squared, or 1/2 kx squared, which is like the harmonic oscillator potential. So these solutions, in some sense, are always like local. They can be used to locally approximate other things in physics. So it's the constant coefficient case is really important, and it's more often than not all you need. So I think God has been very kind to us in that regard, making the world understandable before we had a bunch more math that we don't have.
So not like
not like what I'm about to show you.
Oh, okay.
Yeah.
What were you doing before with lines where you assume the coefficients were functions?
Now I'm going to go back to that, series solutions. And so I do think we're going to focus on the n equals 2 problem. So, and the typical nomenclature here is something like this. Oh man. What is that? Belu, do you remember? What is our standard notation here? I think it's y prime prime plus py prime plus qy equals to 0. I think that's it. So here, make it famous. Oops, use a joke twice. Sorry. Here, P and Q are functions, okay? And let's say of x, we'll use x, all right, as our independent variable. So just to give you an example, I'm going to give you an example before I try to say anything general. I'm probably not going to say much general here, actually. There's just a couple of theorems I can tell you. So let me just get to it. Suppose you wanted to solve, and we can already solve this, right? But let's solve it again. Y prime prime plus y equals to 0. All right, you're like, well, I know sine and cosine are solutions to that. Good, that's true. But what if we didn't know that? Another thing you might have tried would be, well, in calculus 2, I learned a series. I learned power series, right? So I might suppose that I could guess a power series solution to this. So my guess, my Ansatz, if you like, German for guess, y is equal to a sum, k equals 0 to infinity of a sub k x to the k power.
What is Ansatz?
Guess. And fine, I'll use, my k's aren't too pretty. Maybe I should use n instead. I'm going to use n, if you guys can forgive me. N equals 0, a sub n, x to the n. There, it's easier to look at. Okay, so what's y prime? N equals 1 to infinity, right? Of n, a sub n, x to the n minus 1. Why did I drop the n equals 0 term? Well, n equals 0 is a constant, so that differentiates to 0, so I can drop that out. What's y prime prime? Yeah, sum n equals 2 to infinity of n times n minus 1 times a sub n, x to the n minus 2. All right. Where am I going? I'm going to plug this guess back into the differential equation, right? And then in order to make this calculation work, I'm going to need to rewrite both of these infinite series in terms of the same kind of presentation. So factoring works only if I have, if I have x squared and x squared plus squared, and I have plus x squared. I mean, I need to be able to factor out, like, that's not the right way to say it. I need to be able to see a common power in order to do factoring. I'm not making my case very quickly. Let's think of this as being a new variable is my point. Let's call this thing something else. I don't know, j. So j equals to n minus 2. If I do that, if n equals to 2, then j equals to what? 0. And what else can I say? N is equal to j plus 2, right? So with that change of notation, this becomes the sum j equals 0 to infinity. I mean, infinity minus 2 is still infinity, right? So we're okay there.
Smaller.
The smaller infinity, if you say so. Who am I to argue with infinity? Let's see here. J plus 2, and then that's j plus 1, right? Because n is j plus 2 and n minus 1 is j plus 1. A sub n is a sub j plus 2, and then I've got x to the j, right? Of course, in retrospect, you see I could have just as well written the original sum. This is also equal to a sum. Sorry, using green. You can get over it, right, Belu? Is it gonna be okay? Okay, she'll allow it. It's good. So that way I make this and this match. So when I plug them in, I've got y prime prime plus y equals to 0, right? And that gives me what? That gives me a sum. J equals 0. I'm going to skip a step and just go ahead and factor stuff out. The y prime prime, it gives me j plus 2 times j plus 1 times a sub j plus 2, and then plus a sub j, all times x to the j, right? I hope you see what I did there. I used both of the things I underlined in green just a second ago. Now, the only way that series can be 0 like that is if every one of the coefficients separately vanishes to be 0, right? So that then tells me that for all j, 0, 1, 2, forever and ever and ever, I must have this condition that a sub j plus 2 is equal to minus a sub j divided by j1 plus j2. So I get this recurrence relation, right? That links the even coefficients and the odd coefficients as it happens, right? So if we start with j equal to 0, we've got a sub 0, right? Then j equals to 2, what does that give us? Well, a sub 2 is equal to minus a sub 0 divided by what? 2. Yeah. J equals 4 is what? Four times 3, right? Which, by the way, is what? Minus 1 squared a0 over 4 times 3 times 2. Or if you wanted to make it look a little bit more suspicious, maybe I should write this as 2 times 1. Maybe I should write this as 4 times 2 times 2 times 1. J equals 6, what do we get? So you plug that back in, you get minus 1 cubed, a sub naught, over 6 times 5 times 4 times 3 times 2 times 1, right? This is differential equations. I'm not really looking for a proof as much as I'm looking for pattern recognition. So this is enough for you guys to see that a sub 2j is equal to minus 1 to the j times a sub naught over 2j factorial.
If you want to prove it, you can use induction.
Yeah, yeah. It wouldn't be hard, it's just we don't need to. By custom. Avoidance of proof by mathematical custom. It's actually a thing. Okay, anyway, the same almost exact argument goes through for odd powers likewise. Right? A sub 2j plus 1 is equal to minus 1 to the j, a sub 1. Do I have that right? 0, 0. Yeah, okay. Let me think about this for a second. When j equals 0, I've got 1 here. Yeah, okay, it's good. 2j plus 1. So you see what we have then. Put it all together. What is our solution? Y is equal to a sum. J equals 0 to infinity of a sub 0 minus 1 to the j over 2j factorial plus the sum j equals 0 to infinity a sub 1 minus 1 to the j over 2j plus 1 factorial. Oh, and I'm missing something. What am I missing? Kind of very important stuff I'm missing right now in these formulas. Oh, sadness. My what? Not the constants, the other thing. I'm missing my x's. So the constants are there. They're just they're a naught, and so this is x to the 2j, and of course there's an x to the 2j plus 1 here. Now, if you rewrite this, what you have is a naught, and I'm going to rewrite this sum out so maybe more people recognize it. This is 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th plus da da da, right? And then plus a1, and that's x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus da da da. But I hope you recognize, yeah, that's cosine x, and that's sine x. So we have we've recovered the sine. Belu, I think you need to. Did you move over there? Can you see it? So we have derived, separate from our previous work, now that cosine and sine appear as solutions to this y prime prime plus y equals 0 equation. In fact, some people take the perspective as follows. They say that this differential equation, in fact, defines sine and cosine. You can take that. They can take this differential equation, the solution set of this differential equation, as being a definition for sine and cosine. If you take that viewpoint, you essentially have a definition for sine and cosine which is completely devoid of geometry and is completely based on analysis, which allows you to verify things that are geometrically claimed without any direct use of geometry. It's a very powerful observation.
So just, if you wanted to do that, you would just solve like sine and say sine equal to whatever.
You'd say sine is the solution to y prime prime plus y equal to 0 such that y of 0 is 1. Y of 0 is 0 and y prime of 0 is 1. And conversely for cosine, you'd say or you could say it's the odd solution and that's the even solution, equivalently. Something nice to notice about power series, something you should know. Even functions have even power series. Odd functions have odd power series. That's a very useful observation sometimes. Okay, so, I sometimes teach this in Calc 2, right? Because what do you need to do this? Time, energy, the belief that it can be done, right? If you've got those three things, there's hope.
You mean, are you talking about physics stuff or just?
I'm talking about solving an equation like this using a power series substitution. Yeah. Now, it's a pain, right? Obviously, our previous technique of solving this is way, way faster. But we can solve a variety of equations that are more complicated than this. Let's look at some.
The one you wrote up there with E to X.
Yeah, for example, that one. Let's look at that one. Now, sometimes I don't ask for the whole solution. This is, the best thing that happens for us is when we find the complete power series solution. But oftentimes we're only interested in a partial solution, right? So another example you might look at would be something like you said, Landon, y prime plus e to the x, y prime, was it? Plus y equal to 0. We could look for a solution to that. Let's not look for a solution. Let's not look for the general solution to that. That would be tedious. Let's look for the first few non-trivial terms in the solution. Okay, that's a useful exercise for us. So we make our usual guess. Y is equal to a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus dot dot dot. I'll just keep that many.
You had 3y. I don't know if that makes sense.
No. I mean, I could put a 3 there, but that would just clutter things. I'll leave it y. It's fine. So you guess the power series. You differentiate the thing. Differentiate it again. Right. Decide what order you're going to keep things to. All right. Because I'm trying not to drag this on too long, this example, I'm just going to keep the quadratic order. So what I want to do is collect all terms in y prime prime plus e to the x y prime. And let me rewrite that a little bit. What is e to the x? E to the x is 1 plus x plus 1/2 x squared plus dot dot dot, right? I have to replace e to the x with its power series expansion. By the way, I am looking for the first few terms in the power series expansion, the power series solution centered at 0 too. That should be emphasized. You could look for solutions centered somewhere else. Then you'd have to look at like x minus a or x minus x naught powers of that. Let's not do that. Plus y equals to 0, right? And I don't usually, I try not to write everything out. I try to let thinking rather than writing help me out at this point. Because writing is unreliable, but thinking is less unreliable for most of us, hopefully. I don't know, as you look at this, you can just ask yourself the question, what are the constant terms? So start with constant terms. What are constant terms in this? From y prime prime, I have 2a2, right? So let's call this thing star. And let's just think about star has constant, star constant. What are the constants in star? Y prime prime has 2a2. Are you getting this, Belu? The only way I can get a constant from the y prime is this 1. 1 times what? Right, so plus a1. And then the only place I can get a constant from y is what? A naught, right? So that has to be equal to 0. How about the x's? What do we get there? From y prime prime, I get 6a3. And then I got to think a little bit. From the middle term, I get 1 times the 3, I get plus 3a3. Do you see that? That comes from the 1 times this term. Oh yeah, sorry. Like I said, sometimes the thinking works. 2a2, thank you. I'm glad you found that now. Oh, okay, so 2a2. Actually, if I make a mistake here, I never know if I made it. That's one of the kind of sad things about this whole technique. If you make mistakes, there's really no way for you to check your answer for the most part. Unless some initial conditions you're matching, but in that case you can still fool yourself. It's kind of like differentiation in some sense. Like, how can you check a derivative?
You go back and check every little step.
Okay, there you go. That's a good answer, Len. So 2a2, where else can we get x from though? We can get x times a1. So we have plus a1, right? And then how about from the y term? From the y we get a1, right? How about star x squared? Well, oh man. So So it begins. What's the next thing? This is 3 times 2. The next one is, oh man, 12, right? 12a4x squared. Is that right? I think that's right. This is 2 times 1. That's 3 times 2. This is 3 times, this is 2 times 3. This is 3 times 4. It's 12. So x to the 4th differentiated twice. 4x cubed, 12x squared, yeah. The a4 rides along. So when I look at x squared, I get 12a4 from the y prime prime term, right? And then where else do I get an x squared term? From here, right? So one place I can get it is from the x squared divided by 2 times the constant term in y prime. So that gives me plus a1 over 2, right? Then if I look at x times x term in y prime, I get plus 2a2. And then if I look at the 1 times plus the 3a3 finally, that I wanted to use the other time, but I was wrong. I think that's it for the middle term. There's those 3. But you see why this is nasty, Landon, is there gets to be more and more and more and more of those cross terms as you go higher and higher and higher from the Cauchy product of these power series. Then what's y has what? Plus a2, right? So this is pretty nasty problem. To make it nicer for us to understand, how can I say this? Well, I guess I won't try to do that. This is what this tells me something, though. It tells me what a2 is equal to a naught plus a1 over 2. I need a minus. And let's see, this next one tells me what? A3. But you know what? I don't care. Well, I mean, I guess it's useful to do. A3 is what? Minus 2a2. But what was minus 2a2? See that? 2a2 is minus a1 minus a naught. So this actually becomes what? Yeah, a1 minus a naught. Which do you think it is?
Should be negative a naught minus a naught. The top term is going to be...
Fine. I'll write it out. 2a2 minus 2. Oh, these are a1. These are both a1s, aren't they? So minus 2a1, all divided by... I'm an idiot. So there's minuses on both of these, right? And then 6. But this